Let's leave proteins for a little while and then talk about lipids. Fats, sterols, you're probably familiar with the term fat or cholesterol, right? Lipids are a broad class of molecules, and I just wanted to introduce you to them. And again, this is sort of by way of getting you used to looking at these molecular structures, even though you've probably never seen them before. Something that we can point out now, let's just talk about fatty acids for a minute. Something that we can point out now is the development of a sort of a chemical intuition. We see these oxygens here. That's telling us that these are polar. Oxygen is a polar atom, electronegative atom. This is a polar element or a polar portion of this molecule. Whereas remember what these vertices imply, there's a carbon and two hydrogens that are implicit there. The carbons are nonpolar. So this molecule is something has interesting characteristic in that it's got this polar end and a nonpolar end. That gives rise to some very important structure and function as we go on. So fatty acids have a polar end and a nonpolar end. Sorry, a polar end and a nonpolar end. That's one form of lipid. For storage of fat, we typically will see fatty acids stored in triglycerides. And I think it's easy for you to see that this fatty acid here has been stored or esterified into a triglyceride. We got 1, 2, 3 fatty acid chains linked through this blue. In blue here I've drawn the glycerol backbone. So this is a triglyceride for that glycerol backbone. And again, that's called esterification. We've linked 3 fatty acids to the glycerol backbone. Okay, and here I haven't implied the carbons, I've actually drawn them. So you can see that the carbon is bound to 4 partners, 2 hydrogens, 1 other carbon, 1 to this oxygen. Okay, so that's the common storage form, and it's very, very nonpolar, forming oil or fat droplets. Turn to the glycerophospholipids here, third from the left. You can see again that blue glycerol backbone, and only 2 of the carbons now are esterified with fatty acids. The third is modified with a phosphoryl head group. So this is a large polar head group. The difference here is that we've got 2 nonpolar modifications and 1 polar modification. This makes the glycerophospholipids pretty important for, or phospholipids in general, as pretty important for cooking as emulsifiers. So they're able to both interact with a water phase and with an oily phase. And as we'll see, that becomes very important in much of the work that we're going to do in the kitchen. Okay, finally, sterols. So this actually on the right here is cholesterol, but this is what I'm trying to get across here, though, is that this core structure of 4 rings uh, is a commonly used platform for lots of other lipids as well as steroid hormones. What we see here, again, carbons implied at each of these vertices is 4 rings fused together, forming a very rigid and fairly planar structure. And then we can modify those in a number of different ways to make them more polar or more nonpolar. Again, lots of carbons, no oxygens or nitrogens, telling us that's nonpolar. This hydroxyl telling us that's fairly polar. So cholesterol and other sterols are used to modify the chemical and physical characteristics of lipid mixtures. Okay, so going back to the phospholipids for a second, lipid organization again involves the hydrophobic effect. So when we dissolve lipids in water, well, what happens is that we form these interesting structures. Again, nonpolar, here I've drawn a cartoon, these nonpolar tails want to sequester themselves from the watery environment, and so we'll form something like this sort of liposome in which all of the tail groups are facing inward, hiding them effectively from water, and then the polar head groups are on the exterior, able to interact with water. You could imagine this as a slice through a three-dimensional sphere. In the middle here, we're looking at a lipid bilayer. Same kind of idea. Those tail groups are pointing inwards again, but now we form 2 leaflets on the exterior of each, of which is again, a polar head group, forming favorable interactions with water. Another iteration is this micelle, in which we see not a nonpolar core, but actually that that double bilayer or that bilayer wrapping around and forming a three-dimensional structure that encloses an aqueous environment in the middle. And so this is starting to look something like a lot like what a living cell membrane might look like. So again, self-organization is a big theme in biological structure, and we will make use of that self-organization many times in the kitchen. Here's a video, molecular dynamics simulation of a lipid bilayer. Let's just watch it. So what do we see? We see the fatty acid chains pointing inward towards each other, not really moving around a whole heck of a lot, at least not laterally. They're sort of vibrating a lot in place, and then but staying more or less where they are. So lots of localized motion. Well, this is interesting. We can what you can see is that these lipid chains are packed together fairly nicely, and this packing ability is another physical characteristic that I want to talk about. And this brings us to the idea of lipid saturation and the melting temperature of lipids. So you've probably all heard of and thought about the health effects, maybe benefits or of saturated or unsaturated fats in your foods. And of course, temperature and heat plays an important role in cooking. So we're going to consider both of those before we leave fats for a second. So fats versus oils. We'll encounter both of these in the kitchen, and in both cases we're referring to that triglyceride form. Remember, 3 fatty acids esterifying that glycerol backbone. Whether they're fat or oil, right? That's really a terminology that's used in the kitchen to denote whether we're referring to a solid or a liquid. So if at room temperature, remember the temperature is always relative, but at room temperature, let's say 75 degrees or so Fahrenheit, 25 centigrade, fats are the solids and oils are the liquids. Well, what chemically determines that melting temperature? It depends on the degree of saturation, like you've heard before. A saturated lipid is one in which between all the carbon bonds have a single bond between them. All the carbon atoms share a single bond between them. So each of those carbons is saturated. An unsaturated bond is a double bond or maybe a triple bond. So in an unsaturated lipid, we see here 1 degree of unsaturation. So here's stearic acid, 18 carbons in this chain. There's that hydrophilic water-loving head group there. All single bonds. Here's oleic acid, also 18 carbons, but now we have 1 unsaturated bond, 1 double bond, and I think that's between lipids, carbons 9 and 10 from the omega or end carbon. So what we can see just by glancing at these pictures is that the double bond or that unsaturation induces a kink in the lipid itself. And it's this physical change induced by that chemical structure that changes the melting temperature. So what we saw in that previous slide was that those nice long saturated lipids packed together quite nicely, whereas these unsaturated lipids with kinks don't pack together well, and that packing changes the melting temperature. So the closer they're interacting with each other, forming those nice firm van der Waals interactions with each other, the higher that melting temperature. That is to say, the fat stays solid at a higher temperature. So for stearic acid, let's look over here on the left. Here's a graph of temperature versus number of double bonds, or degree of saturation, if you will. And the saturated fat, stearic acid, melts only at 70 degrees. So think of the butter sitting on your countertop. Most of the time, all through the winter for sure, it's going to stay solid. If we introduce 1 degree of unsaturation, that temperature drops a huge amount, 70 degrees to maybe 10 or 15 degrees in oleic acid. So now we're an oil, right? We're a liquid at room temperature. We're melted by the time before we get to 25 degrees centigrade. Introduce another degree of saturation and another, then you're going to be pretty much an oil even at very cold temperatures. So that, again, the number and the extent of those kinks changes the chemical characteristic of the lipid mixture. And sometimes these fats and oils can be very complicated mixtures. Most of the time, in fact, they are going to be fairly complex. This is a sort of a complicated slide, so let me try to break it down for us. Here we're looking at the composition of fatty acids in 3 different compounds. There's a liquid, olive oil, butter, soft solid at room temperature, beef fat considered a hard solid. So we're looking at these 3 and looking at the relative composition of saturated, dark blue, and saturated and dark blue and very light blue lipids and unsaturated lipids making up those. And so what we see is in the liquid, we're mostly unsaturated. Let's say 70% unsaturated lipids composing that mixture. But what we see as we get harder and harder, or higher and higher melting temperatures, is that the total percentage of saturated lipids increases, right? So we see that increasing in beef fat to 50% saturated lipids, resulting in a very hard and solid fat at room temperature. So again, chemical characteristics, gross physical properties. Okay, so last molecule class, or last biological molecule class that we'll talk about, are carbohydrates, probably better known to you as sugars, although we're all familiar now with the term carb from popular culture. Again, I'm going to reiterate, let's not panic when we see these molecular structures if they're unfamiliar to us. We just need, the more we stare at them, the more familiar they'll be and the more happy we'll be about them. But first of all, carbohydrate. So formerly referred to as hydrates of carbon. We have a more complex definitions of them now, but that's good enough for us. For each carbon in the chain, so let's see each carbon in the chain, we have a water molecule associated with it effectively. So we see carbons, 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 carbons. Well, those are looking pretty nonpolar, but every carbon has a hydroxyl or an oxygen attached to it. So overall, carbohydrates are fairly polar molecules. What we're looking at the top here are monosaccharides. That is to say, a single sugar molecule, monosaccharide. In the left side, we see a linear carbohydrate monomer, and on the right, we see a cyclized carbohydrate monomer. And for most monosaccharides in solution, this cyclic form is what we're mostly going to be populating. So you'll frequently see sugars drawn this way or with some simplification here. So a ring structure where we close and one of the ring members is this oxygen. And again, hydroxyl, hydroxyl, hydroxyl all over the place. Fairly polar. Okay, monosaccharides, but we can also link them up to form disaccharides. And you're familiar with some disaccharides. Sucrose, which I've drawn here in the middle panel, is a disaccharide of glucose and fructose, and other disaccharides that you're familiar with are probably fructose and lactose. So we can link these guys together by taking a hydroxyl and linking it up to a carbon on another carbohydrate monomer, right? Monomer, dimer, and trimer. And as we build more and more monomers onto our molecule, we create, again, here's that word, polymer. We create a polymer. So a chain of repeating units. There are lots of glucose polymers in nature. Starch is mostly a plant glucose polymer. Amylose and amylopectin. There's a nice figure in your textbook, page 804, I think, shows you that amylose is an unbranched chain of sugar molecules, glucose molecules. Amylopectin is a highly branched form of polymer. I should note that in proteins we'll almost never see that branching of the polymer, whereas in carbohydrate polymers it's fairly common. In animals, the glucose storage polymer is not amylose or amylopectin or starch, really, it's glycogen, another highly branched carbohydrate or glucose polymer. As well as playing these sugar or energy storage roles like glycogen and starch, there are other glucose or carbohydrate polymers that we observe in nature, cellulose and chitin. Both of those have very interesting characteristics, and you'll know cellulose as an important wood fiber component, and chitin as the exoskeleton of lots of insects, for example. So we can change the chemical nature of the physical nature of the polymer by changing the chemical composition. So I've said here that chitin contains a modified sugar called N-acetylglucosamine. It doesn't matter for our purposes today, but just to underscore this point that subtle chemical modifications change things from change the physical characteristics from something like starch, which is a nice water-soluble molecule, to something like chitin, which forms a component of the hard, waxy shell of insects. So there's our carbohydrates. And we'll be talking a lot about forming and breaking these polymers as we cook our bread, for example, and brew our beer. Let's say something else about carbohydrates, and this sort of brings together a bunch of different ideas and introduces the idea of the enzyme. So I think we're almost done, so let's run through this. Bees do it, let's make high fructose corn syrup. You've probably all heard of high fructose corn syrup. I'm here drawing, it's not exactly the same thing what bees do, but I'm drawing an analogy between what bees do and what food industry does when they create a high fructose corn syrup. So let's introduce to this idea of the sweetness index. There are quantifiable metrics of how sweet a particular carbohydrate is. And the reference standard is sucrose, table sugar. You're familiar with it. Remember, it's a disaccharide of glucose and fructose, sweetness index of 1. Well, sucrose is what bees obtain when they go slurp the nectar out of all of their flowers, along with some other carbohydrates as well, certainly. But what they use is invertase to break that sucrose apart into glucose and fructose. Now, glucose and fructose, the reason for breaking that more complex carbohydrate into the simple monosaccharides is to make it easier to ingest and therefore utilize as a food source. We're doing something slightly different, but before I go on to high fructose corn syrup, let me come back. Invertase is an enzyme. What is an enzyme? It's a protein. I told you that individual sequences of proteins result in individualized functions. Well, this is the name of a particular protein, and it does a chemical job for the bees, and that is simply to break apart the disaccharide into 2 monosaccharides for easy use as a fuel source. Well, when we're making high fructose corn syrup, we're doing something slightly different, but we're also using enzymes in this process. What we start with in this process is starch, right? Doesn't sound very sweet, does it? And it isn't terribly sweet. It is a polymer of glucose, as we said. Now, glucose itself has a sweetness index of 0.7, which is less than sugar, right? Is less than table sugar, sucrose sweetness index of 1. So if we just break that starch polymer down into glucose monomers, which is certainly sweeter than starch, it's still not getting us up to the same sweetness as sucrose. So what we do is employ a whole slew of enzymes in an industrial process. The enzymes first convert the starch polymer to glucose syrup, which has a fairly low sweetness index, but then convert it into 40% fructose, which itself has a much higher sweetness index than table sugar. And so by making a mixture of glucose and fructose, we get a sweet compound that we couldn't simply get from breaking up the starch into glucose on its own. So our goal as industrial chemists is to make a syrup that's very sweet. Slightly different reason than for that which the bees are doing, but we use a similar set of molecules, right? Enzymes, proteins, degrading complex carbohydrates into simple carbohydrates. Okay, I'm going to finish up this lecture with this picture that I love to show. I've given you an introduction into food molecules, proteins, lipids, and carbohydrates. Let's back up a level, though, and say that organisms are composed of all three and some other molecules that we'll meet along the way as well. And organisms are very complex mixtures of all of these. So this is a picture, a painting or cartoon of an E. coli bacterium sliced right through the E. coli bacterium, and we see that there's a cell wall composed of carbohydrates and lipids. There's this tail or flagella made of protein that helps propel the bacterium through the aqueous environment. there's not a nucleus in a bacterium like this, but there is a core full of DNA and proteins interacting with the DNA to turn it into protein. And then there's this very complex environment full of hundreds of different proteins all going about their business. Again, that's defined by their sequence. The point, however, is to remind you that when we're talking about food, we're not talking, in many cases, about uh, simple mixtures of sugars and fats and lipids. We're talking about highly complex structures and highly complex mixtures. And so it is really going to behoove us to think about how each of those play together and how we can control the characteristics of each of those so that we can get the food experience that we want. So until next week, hasta la vista.